Question 10. We are told that 4 metals are irradiated with light of a single frequency. When light of frequency 1.045 times 10 to the 15 Hertz is used, the maximum kinetic energy of emitted electrons is measured and recorded in the table. First, we must define work function. This is the minimum amount of energy required to remove an electron from the surface of a metal to a point just outside the metal. Any extra energy that the electron gains from the photon is converted to kinetic energy according to the photoelectric effect equation. Next, we must give zinc's threshold frequency. The threshold frequency is the minimum frequency of light needed to eject an electron from a metal. At the threshold frequency, the maximum kinetic energy of an emitted electron is 0 joules. Because the maximum kinetic energy is 0 joules, the electrons are being emitted with just enough energy to escape. Therefore, the frequency of light used is exactly equal to the threshold frequency. So from the table, when zinc has a kinetic energy of 0, we can deduce that the threshold frequency of zinc must be equal to the frequency of the incident light, which is 1.045 times 10 to the 15 Hertz. Next, we are asked to compare sodium's work function with cesium's work function. Since the same frequency of light is used for both sodium and cesium, this means that the energy of the photons used for each metal is the same. And so the work function of sodium plus its maximum kinetic energy is equal to the work function of cesium plus its maximum kinetic energy. But from the table, sodium has a smaller maximum kinetic energy with the given frequency of light used. And since the energy of the photons used is the same for each metal, this means that the work function of sodium is larger. Next, we are told that the intensity of light on the metal M is increased, and we are asked if electrons are emitted. We can see that from the initial experiment with the given frequency, electrons for metal M were not ejected. If a certain frequency of light has a corresponding energy equal to the work function of the metal, then electrons are ejected. But intensity of light, which means the number of photons per second, not the energy of the photons, has no effect on whether electrons are emitted. We can say that a higher intensity of light means more photons reach the metal surface per second. But intensity does not affect the energy of the photons. The work function of metal M is still not overcome even at the higher intensity because the frequency has not changed. So no, electrons are not emitted. Even at the higher intensity, the work function of metal M is still not overcome. Next, we are given a diagram of 3 energy levels and their energies in joules. We are told an electron moves from energy level 3 to energy level 1. And we are told a photon is emitted. We are asked what the frequency of the photon is. Since the energy of the emitted photon is equal to the energy gap between energy level 3 and energy level 1, we can calculate the energy of the photon by the difference in these energies. Using the equation energy is equal to Planck's constant times frequency, we can rearrange for frequency and substitute the energy difference in the numerator and Planck's constant from the data sheets into the denominator. Solving, we get a frequency of 6.64 times 10 to the 14 Hertz. Lastly, we are asked whether a photon of energy 2.5 times 10 to the minus 19 joules can be emitted, and we must explain. The energy of an emitted photon is always equal to the energy of the electron transition. We have seen that when an electron transitions from energy level 3 to energy level 1, the difference in energy is 4.4 times 10 to the minus 19 joules. Then a transition between energy levels 3 and 2 would have an energy equal to the difference in the energies of these two levels, and that difference is not equal to 2.5 times 10 to the minus 19 joules. We haven't shown that calculation here, but you could subtract 5.7 times 10 to the minus 19 minus 5.1 times 10 to the minus 19, and we will not get 2.5 times 10 to the minus 19. Likewise, a transition between energy levels 2 and 1 will not give a difference equal to 2.5 times 10 to the minus 19 joules. So none of the possible transitions in this atom, that is, from energy level 3 to 1, or 3 to 2, or 2 to 1, will correspond to this energy. So no, a photon with this energy cannot be emitted.